I would like to welcome everyone to this second day of COVID-5 conference seminar. And today we were a little bit last minute change in the schedule. So I apologize for that, but we will go ahead with our speaker, Renbao Li from Chinese University of Hong Kong. And he's going to talk about the quantum sensing of correlations inaccessible to nonlinear spectroscopy. Renbao, floor is yours. Thank you. Could you unmute yourself?
Okay.
Excellent. Thank you.
Okay. Yeah, thank you, Professor Kagneyan. And of course, thanks to Jihun for inviting me to this event. Okay. So today, my talk is about how to use the quantum sensors to extract correlations that's not accessible to usual nonlinear spectroscopy or some other conventional methods. Okay. So this work was done in collaboration with two of my postdocs, Dr. Ping Wang and Chang Chen. So we know that actually, any information that we can obtain about a physical system, okay, we are talking about the physics. So it's more or less kind of correlations or statistics. Of course, if we want to measure physical quantity, we actually measure the expected value of a certain kind of quantity. In statistics, this is called the first moment or the first order correlation function. Sometimes we also want to study the fluctuation or the variance. So this kind of variance is actually the second moment in statistics or the second order correlation function. Okay. And the famous example of this second order correlation function in physics is the linear response function, which actually is the average of the commutators between two operators. One applied at the early time, another is measured at the later time. Okay. Right. And of course, these kind of correlations have importance in physics, especially if we look at the quantum mechanics. It's actually all about the statistics. So the fundamental of quantum mechanics is summarized by this beautiful formula. That is the variance of position times the variance of the momentum is always greater or equal to h bar over 2. Okay. Right. And this kind of correlations, can also be used to test the quantum foundation, such as the famous Bayer inequality or its later version. Okay. So if we measure two spins, okay, along two sets of coordinates, and then you actually got a correlation. If it's a classical hidden variable theory, and this correlation function is always less than 2, for example, right? But the quantum states can violate this inequality, okay? So that the quantum theory does not have a hidden variable interpretation. Okay. So another test of foundation is this so-called Lagarde-Garg inequalities. So it's actually a set of inequalities about the correlation functions at different times of physical quantity. Okay. And so this is just one of the examples. Right. So conventionally, a widely used method to to measure these correlation functions is the spectroscopy or the nonlinear spectroscopy. Okay. So in the spectroscopy, actually, we kind of apply a force, a classical force to a quantum system, okay, such as the electric field. For example, we can couple an optical field to a quantum system which has operator D, right? So this gives us the interaction. And then the response is the measurement of the change of physical quantity at a later time. Okay, this one can be expanded order by order with respect to this perturbation field. Okay, so such that we can have a first order linear response and the second order response, a third order, okay, so on and so forth. Okay, and we know that all this kind of response of a system is governed by the quantum evolution under this perturbation. If we do the perturbation expansion, okay, the evolution of the density matrix of the system, have the zeroth order, and then the first order, which contains the commutator between this operator and the system density matrix. Okay, and then if you expand it to the second order, then you have the commutator showing up twice, right? And then you can go on. You then have these commutators, to the third order and the fourth order, so on and so forth. But all kinds of nonlinear spectroscopy will give us the correlation functions to arbitrary orders if we want, right? For example, the third order nonlinear spectroscopy is given by these commutators, okay, between the four operators. Basically, it's the operators at 4 times, okay. Right. So a limitation of this nonlinear spectroscopy method is that only the commutator correlation functions can be detected, right? So you cannot detect the correlation function using this nonlinear spectroscopy that contains anti-commutator, for example, right? And so in recent years, there's a new idea in this nonlinear spectroscopy, so called a quantum nonlinear spectroscopy. Basically, so we try to replace the classical perturbation, like the optical field, with a quantum object, such as a quantum light or entangled photons, for example. Okay, and for example, if you use the entangled photons as a probe, one can actually achieve improvement in both the spectral and the temporal resolution. And this, of course, shouldn't be possible if you use the classical light, right? So this is a very interesting, example. Okay, so if we want to know more, there's a very nice review article by Mukerwell and his colleagues. And however, if we use the photons or the photon counts as a method to achieve this kind of correlation functions, there's quite some limitation. Okay, so because the measurement basis of photon states actually cannot be easily chosen. Okay, so there are only a limited sets of measurement bases that you can use. So in general, we can consider a quantum sensor and a target. So this is the so for example, we can consider a spin, a central spin, interacting with many other spins, which are the targets to be detected. Okay, and if we have both of them a quantum system, and then we say that the evolution, because of the interaction between them, will induce entanglement. And then this entanglement will make the measurement on the sensor is actually also a measurement of the target. This measurement of the target is called a Pauli type 2 measurement. And then we look at the correlation functions of the measurements on this measurement. We can see that they are actually related to the correlation functions of the targets. And by choosing the initial state of the sensor and the measurement basis of this sensor, and then we can actually realize the detection of arbitrary correlation functions. Right, so this is the quantum circuits diagram for this sensing process. Suppose we have a sensor denoted by S, has an initial state given by rho S, and also we have a target which is denoted as rho B, and then they have interaction. That's the coupling between the system operator, the sensor operator S, and the target operator B, right? And then after the interaction for a short period of time, okay, and they will establish entanglement between the two systems, and then we do the measurement only on the system, okay. So if this entanglement is weak, or the interaction time is short, and then this measurement on the sensor spin actually is going to be a weak measurement of this bath beam, okay. Right. So the difference between this sensor target interaction and the nonlinear spectroscopy is that now the perturbation actually is a quantum object. It's not a classical force. So S itself is an operator, right? And then if we look at the evolution of the whole system, so again, we still have this density matrix evolves by this commutator between the interaction and the density operator. But however, this interaction contains two operators, right? One is the system, the sensor operator, another is the target operator. So if we try to separate them, you actually have two terms. One contains the anti-commutator between the system, the sensor operator, and the sensor state. another one, and then you times the commutator, between this target operator and the target state, right? So this is just the usual term for a classical probe. But however, because the sensor is a quantum object, so you can also have a commutator between the state of the sensor and its operator S. Now you have this anti-commutator, right? So you have both terms, okay? So that means you can have both the commutator and the anti-commutator showing up in the evolution, okay? And this commutator, of course, is the difference between the exchange orders of the products, which will be zero for the classical quantities, right? And then this anti-commutator is a symmetric arrangement of this product. But this term, however, will not show up if you have a classical probe, right? So that means if by using the quantum sensor, we actually have new opportunities to access all kinds of correlation functions of the target. If we can design the initial state of the sensor and can choose the measurement basis of this sensor, right? So this is a table just to summarize, different kinds of probe and targets, and to see what kind of information can be retrieved by the sensing process. Okay. And suppose we have a classical probe and a classical target, right? So this is just the classical physics, and then we have interaction, and the evolution of the system, the response is actually governed by this so-called Paulson bracket. Okay. And then the accessible information will be all symmetrical arrangement of the quantities. Okay, so this is because of that classical quantities, so the order is not really important. So they are just the usual first moment, the second moment, the third moment, and so on and so forth, right? So that's the what kind of information we can achieve, we can retrieve about the classical system using the classical probe. However, we can also use in a classical field, such as the optical waves, AFM tips, the magnetic resonance coils, right, so on and so forth. Using this kind of classical probes to detect the quantum systems, such as atoms, spins, right, and solid state systems. Okay, and then the interaction, as we learned earlier, right, so it's given by this commutator between the interaction and the quantum system state, right? So this one contains only the commutator between this operator B and the target state. And then the correlation function is just the nonlinear spectroscopy response, so which contains all kinds of commutators, okay, between the operators at different times, right? So that's the one we have talked about. But of course, you can also use a classical probe, such as photons, spins, photons, right, to detect the classical quantities such as gravitation waves, magnetic fields, temperature, right? So this is called a parameter estimation in the sensing field. Okay, and then you can see that now we have the evolution is given by this, right? So there's no evolution of the classical parameter, but only the evolution of the sensor state. Okay, so in this case, we also have the correlation functions the same as for the classical probe interacting a classical target. Okay, so because this is the only correlation function that we can have for a classical object, right? And then you can see that in this case, the quantum sensing actually is just to does not obtain any new information about the classical objects, but just to enhance the measurement, right? The most interesting part is this quantum sensor to detect the quantum object, such as we use the photons, spins, or photons to detect the photons, spins, and the photons, right? So this is the case we have just discussed. So we have this interaction between two quantum objects, S and B, and then we have this commutator, between this interaction and the whole system, and then it can be separated into two parts. So it contains the commutator and times the anticommutator, or the anticommutator times the commutator, right? And then this way we can obtain all kinds of correlation functions that could contains one commutator and one anticommutator, right? So on and so forth. Okay. Right. So the general scheme is like this one. So we can have a sensor prepared, for example, in the initial state X, we assume this is a spin half. So x is just the spin state in the x direction. And then this spin actually can be affected by a classical field, but can also be coupled to a quantum object, rho b, right, with interaction SC times this B. And this interaction at different times could be different, right? And then we do the measurement along a certain axis, sigma k. And this can give us results +1 or -1, right? And then we can just keep doing this one, and then we can take 3, for example, measurements, and then look at the correlation between them, right? So this is called, for example, third order correlation function, GIJK. Of course, you can also choose the second order or fourth order to look at the different correlation functions. And then by choosing the initial state to be X or to be Y, I'm choosing the measurement basis to be X, Y, Z, or any other directions, we can actually obtain different kinds of correlation functions of this target. Okay, so these are just a few examples. Okay, and depending on the measurement basis. Okay, so for the details, and so we have listed all kinds of possibilities in this PRR paper about 2 years ago. Okay, right. So this is one of the example for the application. Okay, so if we just choose the initial state to be X and then do the measurement of Y, so this basically measures how fast this sensor spin is rotating, right? So if it's rotated to the Y direction, you can see that the measurement will be always +1. If it's rotated to the Z, -Y direction, you got a -1, right? So depending on how strong is the interaction, the field, and then you can have different probabilities to measure this one to be +1, -1. And then you do the correlations of them. You can actually look at the correlation of this field at different times, right? And we can make this interaction to be very short. There is a weak measurement. And then the correlation function to give us this kind of oscillating, because of the spin notation. If we choose the natural magnetic center spin as the sensor and the carbon-13 as the target to be probed, so we can see that this oscillating frequency is just the frequency of the carbon-13 spin. And then there's a decay, and this decay is because of the measurement induced the feedback. So that's the measurement induced the decoherence. Okay, and of course we can make this measurement to weaker and weaker, and then to make this decay is very small. And then we do the Fourier transform, you're gonna have a very sharp peak. So that means we're gonna have very good spectral resolution. Okay, so this is the best spectral resolution people have achieved. Okay, for single Euclid spin magnetic resonance. So you can see this is 3.4 Hertz. Using this one, people can easily distinguish 2 carbon-13 at different chemical environment. That means they have different distance from the natural magnetic center. Both of them are actually very weakly coupled. Okay, so this was done in Stuttgart by my collaborators. And also you can use high order correlation functions to distinguish different kinds of noises. We know that if you only look at the second order correlation functions, you just have a frequency, you just have the amplitude. But this could be the same for all kinds of noise, right? You can have a Gaussian noise, telegraph noise, or random phased AC field. You can have noise from a quantum object, such as a single spin, or 2 spin, or spin 1, spin half, and so on and so forth, right? So you can have different kinds of noise sources. And if we only look at the second order correlation functions, actually you don't see much difference. So at least you don't see any qualitatively difference. Okay, and however, if we look at the third order correlation function, you can see that the Gaussian noise have this 12 peaks in the frequency domain. Okay, so so we do the Fourier transform of 2 frequencies between IJ and JK. Okay, and then if it's telegraph noise, you can only see 4 peaks. Okay, and for the random phased AC field, you see 6 peaks. Okay, so they are actually they're qualitatively different, right? So they have fingerprints patterns, so you can immediately tell what kind of noises they are by looking at this third order correlation functions. And if it's quantum spin, actually it's also very interesting. If I have one spin, you know that one spin is very similar to the telegraph noise. Okay, so you can see that the spectrum actually are very close. However, if we really look at them, if we compare the second order and third order, they still are quite different. Okay, so you can see that the strength will be very different. And if we look at the 2 spins, and this pattern is also distinct. And if I have more and more spins, we know that if I have more and more independent telegraph noises, and then you're going to approach the Gaussian noise, right? So if you look at 6 spins, actually the pattern, the frequency pattern is very similar to the Gaussian noise. Okay, so anyway, by taking a look of this third order correlation functions, actually we can distinguish noises of different types, being classical or quantum, the Gaussian or telegraph, and so on and so forth, right? And so this one actually has been partially verified by the experiments in my collaborators group in Stuttgart. Right, so this is another example that we can apply this quantum correlation measurement. So in the usual sensing task, so we have a sensor spin. Okay, it interacts with a target spin, which can be, for example, precise in about a B field with frequency omega 0. Right, with the interaction given by an effective field for this target spin, which is just hyperfine coupling constant A, for example, if it's electron and nuclear spin, right, and times the operator of this target spin. And then you look at the correlation function, second order correlation function, we'll see a peak right here, right? But in the reality, there are always noises, classical noises, also affected this sensor spin. So that means there will be another field, big BC, that's a classical noise. So if you look at the correlation functions of both fields together, actually you see something like this one, okay? So it's very difficult, it's almost impossible for us to identify which peak is from the target spin, right? Because they could have a similar strength, okay? So there's no signal to noise, enough signal to noise ratio, okay? So we cannot identify, the target spin in this classical noise background. But however, remember, so if you look at the higher order correlation functions, the quantum object could have different kinds of correlation functions, right? But the classical noise can only have anti-commutator correlation functions. So that means if we measure the correlation functions such as this one, which contains the anti-commutator and then commutator and the commutator and the anti-commutator, and then for the classical noise, this will be absolutely zero. And for the quantum noise, so this will be non-zero. So that means this will be a background-free detection, right? So this is the schematic. So if you look at the spectrum of this fourth order correlation function, which contains commutator and anti-commutator, you are supposed to see no contribution from this classical noise. And this way to remove the noise effect actually is universal. It does not depend on the statistics. It could be Gaussian or non-Gaussian telegraph, right? It does not depend on the spectral properties. It could be white or it could be color, right? It could be omega noise, right? It does not depend on the strength of the noise either, right? It could be strong or weak, right? So this is a universal way to exclude the effects of the classical noise background in the sensing task, okay? It's totally new, okay? And then indeed, we tested this one for MV center coupled to a nuclear spin together with a background noise. And you can see that the classical noise give us a spectrum, and the quantum target also give us a spectrum, okay? This is just the discrete Fourier transform. You can see that, at the omega 0, this just gives us a sharp peak, right? Okay, but with the broadening because of the decay. And then you can see that no matter how you increase the number of measurements, so that means no matter how you increase the data acquisition time, so the classical noise always increase proportionally. That means if you have a classical noise too strong, or if you have your a broadening of the quantum target too big, that means the height of this peak will be limited, and then the signal to noise ratio will not be sufficient, right? So that means if we plot the data acquisition time required to see enough signal to noise ratio as a function of the classical noise strength SC and the broadening of your quantum target peak resonance, you can see that when 8 of them are too strong, okay, so when both of them are too strong, you can see no signal to noise ratio at all, no matter how long you increase the data acquisition time, okay. So there is a blind spot for this classical, for this second order correlation sensing. This actually is a method used widely in the quantum sensing tasks, okay. And however, if we look at the fourth order correlation function, okay, and you can see that no matter how strong is the noise, no matter how broad is your the peak of this quantum target resonance, you can always increase the measurement time. Okay, of course, eventually it will be not really economic. Okay, but you know, in principle, you can always increase the measurement time so that you can see sufficient signal to noise ratio, right? So make this one is always greater than 1, so that you can see the contribution from this quantum target, right? So this make a classical noise-free detection, okay, by the fourth order quantum correlation function. Okay. Of course, you can also use other kinds of correlation functions, okay, to realize similar, you know, objectives. Right. So this is a summary of my talk. So basically, so I've tried to introduce this idea of quantum nonlinear spectroscopy using you know, sequential measurement and look at the correlation functions. We see that the arbitrary correlation functions of quantum targets actually can be extracted. Right. So I take a few examples. One particular example is the application to classical noise-free detection of a quantum object. Okay. And then the ongoing research is trying to use these high-order quantum correlation functions to test, for example, quantum foundation, such as the high-order Lagrange inequalities. Okay. And also could provide a new approach to quantum many-body physics, because the conventional spectroscopy can only detect certain kinds of correlation functions, but now we have a way to look at the new kinds of correlation functions. So that will provide you know, open a new window, you know, to the you know, properties of the states in quantum many-body systems. Okay, thank you very much.
Thank you very much for introducing this new approach to quantum sensing. Very, very interesting presentation. Thank you. And then before I go through the question on the chat, I just would like to remind everyone, I think, which I forgot in the beginning, these talks will be streamed on YouTube and they will be also available to watch afterwards on demand. So I believe you can see the chat and then, but I think it will be a good idea to read the question to everyone. So the question is from Ekrem Taha, and are there any protocols to prevent decoupling between the sensor spin and the mounted environmental spins, which are in proximity to target spatially?
So could you
yeah, I mean, you can also see it on the chat, I believe, but I can repeat it. So he's trying to ask that. Okay. He's most interested to hear about, is there any protocols to prevent decoupling between the sensor spin and the unmounted environmental spins?
I see. Indeed, there are many spins in the background, and in principle, they are all quantum, right? So first of all, if the coupling strength is much weaker than the one that we are interested in, okay? So you know, if you have a magnet, in principle, the magnet is also made of many spins, right? So, but those interactions is extremely weak, and then they all contribute actually. So I didn't talk in details, but however, you can imagine that because of these commutators, so only the spins, only the quantum operator from the same quantum object will have non-zero commutators, right? So that means so the signal is proportional to the quantum signal is proportional to the number of the spins. But however, the order, if we go to the fourth order, third order, right? So the correlation function is proportional to the interaction strength to the third order, fourth order. Okay, we know that the number of spins times the coupling strength squared is usually a constant. So that means this kind of weak coupled background spins will contribute almost zero signal. So this is the one thing. Secondly, if the spin are not that weakly coupled to the center spin, so in principle you can detect all of them. But if you really want to just detect a certain kind of spins, suppose I want to detect the spin only at a certain frequency, what can we do? So we can use, for example, dynamic decoupling sequence, so that only the spin at this frequency would interact effectively with the sensor. And then we can decouple those spins which do not have the right frequencies, right? So that's another way to to exclude the spins which are not that weakly coupled to the sensor. Okay. And there, of course, there is some limitation. There will be a spectral resolution, right? So if they are, the dynamic decoupling spectral resolution is given by the 1 level T2. T2 is the coherence time of the sensor. So you cannot do much better than exclude the spins, of different frequencies in that sense. Okay. But however, as you can see that in this spectrum, you can see that if you have 2 spins, you can actually see a different pattern in the spectrum. Okay, so that means by looking at the different patterns, you can also tell yourself that there are 1 spin or 2 spins. Okay, and then you can deduce like quite some information about the spin system. Okay.
Okay, I think it's really good to hear that there are different options to do that that's available. And the next question is from Jaehoon Bulsai, and he's trying to understand if there's with this information provided, is it possible to improve the coherence via feedback?
It's possible to. I cannot see the chatting.
Chat.
Oh yes, all right. I can see it right now. Okay.
Okay. Is it possible to improve the coherence via feedback with this information?
So in principle, this information can be used to improve the coherence via feedback. Yes, but it's experimentally it's not that easy. Okay, so you need some very fast electronics, for example. Okay, but if it's nuclear spins, probably is doable. In principle, yes. In technically, it's not always convenient to do this.
Okay, I think with that, that's all of the questions I could see as well. So
yeah, I think the time is also up, right?
Yes, thank you very much once more.
Thank you. Okay.
We really appreciate joining us. Thank you.
Thanks a lot. So I'm going to stop sharing.
Yes, please. Thanks. And with that, I would like to introduce the next speaker. Could you please also share in the meantime your... Yes. So the next speaker is from Newcastle University, UK, Ahmet Avşar, and he's going to talk about today experiencing magnetism in a 2-dimensional noble metal dechalcogenide. The floor is yours, please. Thank you.
Okay, so thank you very much. Yes, I'm Ahmet Avşar. I'm a lecturer at Newcastle University in the physics department. So before starting my talk, indeed, I would like to thank the organizing committee for including me into their schedule. So it's really a great pleasure to be here talking about my research. And indeed, this research was conducted at EPFL in the group of Andras Kiss before I moved to Newcastle University. So I will be talking about the extrinsic magnetism in ultra-thin materials. So I understand that it's a bit different than the general focus of the COBIT. So I will be giving some brief background about this material science related to 2-dimensional materials. So, of course, everything started with the discovery of graphene. Researchers from Manchester University in 2004, they had graphite, and then they use a very simple method to get like the ultra thin, like the thinnest material ever can possible at the ambient conditions. And this material called graphene is like just 0.3 nanometer, and it shows like completely different properties once you thin down from bulk into the monolayer. And then they also demonstrate a lot of groundbreaking experiments, and then they got Nobel Prize in 2010, 6 years after the discovery of graphene. So this is like one of the fastest Nobel Prize in the history of, I guess, the Nobel Prize. And indeed, one of the things which was the most interesting about one of the message of graphene was apart from graphite, we have like several other types of the materials which are similarly bonded with each other through these weakly van der Waals bonds. So the question is, can we go into these materials, and again, by thinning down, can we achieve some properties which are absent in the bulk? Okay, so the answer was yes, and right now we have isolated more than hundreds of materials, and these materials they do show like different properties. Some of them are very interesting. So, for instance, like graphene is a semi-metal without any band gap. So we have now all different types of the materials with different band gaps, so small band gap materials and very insulating materials, which is like filling covering this spectra. And indeed, one of the reasons why these 2D materials is the hottest topic in the condensed matter nowadays is indeed you can get also like artificial device like materials. So you can get one of these material and then place on top of other, and then you do get like these heterostructure devices. So why this is important is basically by combining them, either you can compensate the weakness of a material, okay, or you can add like completely new functionalities which are absent in the pristine form. And indeed, the field has been even like going into becoming like more rich recently with the discovery of this Twistronic, and basically it was shown that even like the way that you are aligning these materials, the electronic properties are completely changing. So, for instance, if you get like two semi-metal sheet, okay, and then you place on top of each other, you can get the superconductivity, or you can get like correlated insulators in these materials. So that's one of the reasons that this material system is very interesting. And indeed, since the discovery of graphene, there was always a question, like, can we also get like a monolayer magnet, so a material which has like a spin polarization at the thinnest layer, okay, at the ultimate thickness layer. And the answer was even like it was considered to be like impossible, but later on a group at Washington University and MIT, they demonstrated that a material called chromium iodide, it does show magnetism at the monolayer limit. Okay, so this material is very interesting. At the monolayer and also other odd layers, the material showing is like fully spin polarized. And it was shown that if you have like bilayer, the spin polarization from both layers are canceling each other at the zero field, and then this material become antiferromagnet. And then it was shown that all the materials with the even number of the layers, they do show zero magnetization at zero field. And then once you start to apply a magnetic field above the coercive field, then you can change the magnetization direction of the one of the layer, and then it can become like fully spin polarized again, like you do see here. So these materials, they give us the opportunity to have really like layer dependent magnetism, which is not possible with these conventionally grown materials. Okay, and then soon it was also shown that chromium iodide is not alone. We have very different materials which have this kind of like layer dependent magnetism, but indeed these spin alignments are all different types. So because of the strong competition between the intralayer and interlayer exchange coupling, we have like all this sort of spin alignments. And now we really have like the material systems which have like which are layer dependent magnets, and also they can be changed. They can have like completely different magnetic orientation ordering depending on the material that we will choose. Okay, and indeed these are not the only magnets that we have. The materials that I just showed you, they are intrinsic magnets. And indeed, what you can do is you can also extrinsically induce magnetism in 2D materials as well. So one of the method is called proximity-induced magnetism. What you do is like you get a non-magnetic material and then you place on top of a magnetic material. And if this proximity interaction length is larger than the thickness of the material, then you can induce this magnetic property into this non-magnetic material. For instance, it was shown that if you place graphene on Higgs substrate, you can get anomalous Hall effect in graphene. Okay, and the second method is like dilute magnetism, and in this case, what you do is you do have like you put some atoms on top of these materials, and then they turn into the magnetic materials. And you can, for instance, check like manganese doped gallium arsenide, or even with the 2D materials. Recently, it was shown that if you dope the tungsten dicyanide with vanadium, you can induce the magnetism. And the third approach was defect-induced magnetism. So this was indeed a topic which have been like discussed since the discovery of graphene. So the idea was you have a material, okay, which is non-magnetic in the pristine form, and then you have some sort of defects in this crystalline structure, and then the material turn into a magnetic one. And there are different ways of doing it. And for instance, it was shown that you can have like grain boundaries in specific direction, then you can have the magnetism, or you can apply some strain vacancies, or you can remove some of the atoms, or you can replace the atoms with foreign atoms. Okay, and then so for some of the materials, it was predicted that yes, we can induce the magnetism in this way. But it was experimentally very challenging, because the formation energy of this atom, these defects that induce the magnetism, they are energetically more unfavorable. Okay, so for instance, in the case of the MOS2, it was known that generally like these metal vacancies are the one who are contributing to the magnetic ordering. And you can already see here that the formation energy for this metallic one is much higher than the sulfur. Okay, and another paper came out indeed around 2019, beginning of 2019, and then they say that the metallic vacancy formation for platinum cyanide, it can be much smaller. And then this also brought us to the question of, can we see this defect-induced magnetism in platinum dicyanide? Okay, and yeah, today that's what I will be talking about. I will be dividing my presentation into two halves. First, I will be talking about the electronic structure of this material. I'm putting this because you will also gain some idea why there is an emphasis on going from bulk to the monolayer limit. So what can change? So you will see that this platinum cyanide has like very strongly thickness dependent electronic structure. And then in the second half, I will be discussing about the magnetic ordering in this material with the defects. Okay, so let me start with the ABC of the platinum selenide. Okay, and this platinum selenide is like, unlike the other TMDCs, transition metal dichogenides, which have the phase of 2H. This material has 1TH. Okay, so it's like whenever someone talks about the monolayer of the platinum selenide, what you need to just imagine is you have like a platinum layer, and then there are also like top and bottom selenium layers. And this material, it can be grown through like different methods. So for instance, you can use the chemical vapor deposition, you can do salinization, molecular beam epitaxy, and also chemical vapor transport to grow this material large scale. So this also means that if you want to do any application based on this material, it's doable. So the technology is already there. And this material has indeed different types of the electronic structure. So indeed, for a long time, it was known that the bulk of this material is a metal. It's a semi-metal, okay? And But in 2017, it was discussed that once you go from bulk to the monolar limit, okay, because of the strong interlayer hybridization, a band gap opens at 2-layer. So once you thin down this material to the 2-layer, then the material becomes like a low band gap material, and indeed in monolayer the magnitude of the band gap is even increasing. Okay, and which makes the material especially important for the mid-infrared optoelectronic devices. And another promising thing about this material is it's expected to have very high mobilities. Okay, so it has like a sizable band gap and high mobility, so which could be quite interesting for the transistor applications. And here you can already see that in case platinum selenide is falling into the category with the black phosphorus. Black phosphorus is one of the most studied 2D semiconductor, and indeed platinum selenide is also in the same range of the band gap and also the mobility. But the advantage of the platinum selenide compared to black phosphorus is platinum selenide is air stable. Okay, so I will show you later, but for instance, many of these 2D materials like black phosphorus or chromium iodide, if you isolate them, and then put on a table for half an hour, you just see that the materials are completely disappearing. In the case of the platinum selenide, it has like a long-term stability, even ambient conditions at the monolayer limit. So let me show you a bit of the thickness-dependent electronic structure of this material, like just experimental results. And you can already see that if the material is thicker than 2.5 nanometer, it's like very conductive indeed. And as the thickness start to be reduced, the conductivity start to decrease. And as you can see already here, that as it gets thinner, it starts to give a response to the gate voltage, because the material becomes thinner, and then you can control the carrier concentration through the electric field. Okay, but once you go to the limit below the 2.5 nanometer, what we see is the material turns into a semiconductor. So you can here already see that the material has an off current, and then once you drive the Fermi level from the gap into the conduction band, you do see that the conductivity starts to increase, which is a typical response of a semiconductor. Okay, and getting monolayer for this material was it was extremely challenging, and then we could only get it like last year, and then what we could see is the monolayer of this material. One can say that it's like fully insulating. So it's like a very insulating material. Even application of the high bias, we don't see really a good conductance, and based on the analysis, you can already see that it has this two-dimensional variable range hopping type transport from low temperature to the room temperature with any carrier concentration that we had. So it's an interesting material. It shows metallic, semiconducting, or insulating properties depending on the number of the layers you have. Okay, and we have also used a technique called ionic liquid to measure the band gap of this material. So basically what it does is like it allows you to apply more capacitance, like a more effective electric field. Therefore, you can really go from the conduction band all the way to the valence band. And then by also using some references, at the end of the day, you can just extract the band gap through the transport. So we got the band gap experimental in the order of 2.2 eV. And another interesting thing about this platinum selenide is the material is showing very low contact resistance. Okay, so compared to the other materials, 2D materials, the material is like semi-conductive, and it also suggests that this material itself can be used as a contact material to other semiconductors based on the 2D materials. So now I will be talking about the platinum selenide case for the magnetic response. So indeed, this is the work which brought our attention to this material. So a group in at IMRI in Singapore, they had this prediction that if you have single or double platinum vacancy in this platinum diselenide, the material becomes magnetic. Okay, so basically they predicted the 6 Bohr magneton per defect for monolayer. And as I mentioned before, it was very challenging to get the monolayer to try if this material is really magnetic. And we asked all collaborators at EPFL, Oleg Yazev's group, to calculate if the thicker layers of the platinum selenide is also magnetic. And indeed, we got a lot of interesting insights which help us to understand our experimental results later on as well. So what this theoretical calculations saying is, yes, even in 6 layers, you do see magnetism, but only if you put these impurities on the surfaces. Okay, so if you have these defects within the material, basically the magnetism is quenched. So that was the first result that they got through the calculations. And the second result was, as you increase the thickness, the strength of the magnetism was decreasing. Okay, so basically for monolayer it's like 6 Bohr magneton per defect, and for 6 layers they calculate only 1.2 Bohr magneton per defect. Okay, and then, so this also brought us the question that is it the RKKY type of the interaction that we should expect? Because based on our theoretical predictions, we do see the magnetism only once that these magnetic impurities are on the surface, and then they can only talk to each other through the conduction electrons, and then therefore that could be the origin of the magnetism. Okay, and here how the magnetic exchange coupling depends on the distance between these magnetic impurities. And then we were also lucky enough that time that there was a RPES measurements done on the platinum selenide, which show that Fermi wave vector number, Fermi wave number, and then we input inside, and then what we saw is quite interesting. So this is like a parabolical picture, but it gives a lot of information, as I will be showing you later on about the experimental results. So what it says is, as the thickness of the material is increasing, the strength of the magnetism is decreasing. Okay, and but more interestingly, it shows that if you change just like one layer, you can change the type of the magnetic ordering from ferromagnet to antiferromagnet. So what it does, it says is like adding or removing one layer is sufficient to change the magnetic ordering in this material. And the question was, do we have this kind of really defects, right, in this material? And we don't grow this material in our lab, so we were getting from a manufacturer. But the question was like, are there this type of the defects in these materials? And we had TM studies, and then indeed we have a high concentration of this type of defects in the material. And also there was another study done through the STM, scanning tunnel microscopy, and then it was shown that indeed these platinum vacancies exist in this material in the same type of material grown as in our study. Okay, and then we start to make the devices, and I will tell you in a minute, but we need to do like a comparative study as a function of thickness. Therefore, we wanted to have the same type of the width in all the crystals that we study. And also sometimes we were not seeing the magnetic response that I will be showing in a minute, okay, in the wider samples. So that's why like we choose only the materials which has like a width of less than a micron. And this was the first sample indeed we studied, and then it shows the metallic response as we expect, because the thickness is about 2.5 nanometer, and we start doing the magnetic measurements. So here I just added a short slide for some of the audience who are more familiar with the SQUID or MOC measurements. And this is the typical response you do get with the ferromagnetic samples or with anomalous Hall effect measurements. But if you measure in RXX in longitude, this would be the response that you get for ferromagnetic samples. And if the material is like an antiferromagnetic, and this is how this response would look like on MOG, okay? So you don't have any magnetic ordering near the zero, and then once you go above some coercive fields, yeah, and then the material become completely like completely spin polarized. And then if you would measure the resistance of this device, you would get like 2 Plateau system, right? And that's what we will be looking in our devices. So here, let me show you the results that we got in this sample. And indeed, 5 out of 11 studied devices were showing this kind of responses. If you switch the magnetic field from positive to negative or negative to positive, then you do see this kind of hysteretic behavior. And then indeed, the change in the resistance, it can be as high as 400 ohm with a MR% equivalent of 6%. Okay, and then we could also see that this type of the ferromagnetic ordering persists up to 13 Kelvin. And here we also plotted the change of the device resistance with the temperature, and you can already see this up here, which suggests that the suppression of the spin-dependent scattering. And if you measure, once we measured the other 6 devices out of the 11 we characterized, we saw like completely different types of the response. Right here, this is the response that we see. We do have like 2 Plateau system, okay, and depending on the magnetic field we apply, it's like either at this state or this state, right? And this also kind of like a signature of the magnetic antiferromagnetic type of ordering that we previously saw with the chromium iodide. So if we combine all the measurements that we were doing, we got indeed like an interesting observation. So you could already see these black ones, the black dots are ferromagnetic ordering, and then the red ones are antiferromagnetic ordering. And what we do see is like they're alternating, okay, and device to device, and it looks like it's depending on the thickness, and the magnitude is decreasing as you increase the thickness. And indeed, above 20 nanometer, we never managed to probe any magnetism, even at the lowest temperature. And this looks very similar to this simple RQKY picture we had. And the question is like, really, do we have like layer dependent magnetism in this material? And especially our PhD student that time, now he's a doctor, Alberto, he worked very hard to isolate these materials. And then what we were looking is getting 2 materials next to each other, but one of them is like just 1 layer thicker than the other one. And then we finally get these materials, and then these are like 2 platinum cyanide ribbons with a thickness just varying 1 layer. Okay, and if you measure the magnetic response in these devices, you have again this 2 Plateau system. But if you do measure at the next device, then we do see this ferromagnetic type of the response. So it looked like we had a layer dependent magnetism. By just changing 1 layer, the magnetic ordering is changing in here. And indeed, we had also a chance to check in another device. So this is like a platinum cyanide. I think it's not very obvious here, but we have at the positions where we have these arrows, we have like indeed 1 step height materials. Okay, so this AFM scanner you could already see, and we measured also the magnetic response in this device. And what we could see is indeed like it's a combination of the both magnetic and antiferromagnetic types of the signal that we see in the same device. we do believe that some contribution is coming from these layers, which have addition layer, and the other ones have just a ferromagnetic response. And recently, we have also shown that we have also studied the monolayer and bilayer platinum selenide, and we were curious if the magnetic ordering persists down to the monolayer. But again, like measuring these devices with the transport at the mono limit is very challenging because they are extremely resistive. So what we did is we put a graphene on top, and then we use graphene as a probe, as a sensor to sense this magnetic response of the substrate. And what we do see is, like, if you don't have any platinum selenide under the graphene, you do have weak localization response, which is typical for graphene. Okay, and what we see is if you have one layer of platinum selenide and two layers of platinum selenide, we do have again like different types of the magnetic ordering, which can be probed through the graphene. Okay, so let me also briefly tell you. There is also a possibility of having a magnetic response in platinum selenide if you have kind of like some foreign atoms. Okay, so there were some predictions, calculations. They were saying that if the material is doped with the transition metal atoms, then you might have the magnetism. So the question was, is it possible that our materials are contaminated with the foreign atoms, and that's why we do see this magnetic response. We work very hard to exclude this. Indeed, we did like a lot of TEM scanning and XRD, EDX, ICP-MS, and Raman characterization, and we couldn't detect any extrinsic atoms. So we do believe that the origin of this signal is coming from the defects in platinum selenide, and we also believe that it depends on the concentration of these defects. Okay, so I think I have only a few minutes left, and I will be briefly discussing why this material is interesting. Okay, so this platinum selenide, first of all, it can be grown large scale, and then it can be also transferred. So from one substrate to another one, so it could be used in the applications, and also you can already see that it's very air stable. So even like 3 months after the material is still stable, and the magnetic response after 250 degrees of annealing is still stable. But if you compare, for instance, any of these intrinsic magnets that I introduced at the beginning of my talk, you will see that they are extremely air sensitive. So if you have a chromium iodide, and if you isolate it, and if you expose to the air in 80 seconds, as you can see here, it completely degrades. Okay, disappears. And even if you encapsulate, the encapsulation is only protecting it for only several hours, even its properties changing along the way. And another cool thing about this magnetic ordering, this extrinsic magnetism in the platinum selenide is depending on the defect concentration, you can really manipulate also the magnetism. So it gives you an opportunity to do atom by atom the control of the magnetic ordering in these materials. So depending on if you are growing your material under the selenium rich environment or platinum rich environment, then you do have different type of the concentration. Okay, and the material is also layer dependent electronic structure, so therefore it can be used as a magnetic insulator or conducting magnet in several applications. And in summary, the material is showing like thickness dependent properties. It's metal in bulk, semiconductor in 2.5 nanometer below, and monolayer insulator. And the material is also showing the magnetic response above 20, below 20 nanometer, and it looked like it has a thickness dependent magnetic ordering. And let me put this last slide, and indeed Isidore Rabi, he was asked at Columbia University about this material science, and he said that there is no need to study physics of dirt at Columbia Physics at that time. But I think this study is already showing that if you can use these defects in a good manner, then you can induce some properties, interesting properties, which are absent in their pristine form. And with that, I would like to thank my collaborators, especially of course the Prof. Andras Kis, who is leading that group, and also the theoretical support from Oleg Yazev and his PhD student Michele. Yeah, so that's all. Thank you very much.
Okay, thank you very much for this very interesting topic on and introducing us the magnetic properties of 2D materials. Actually, there was an earlier question on the chat, but let me start with the last one first. So again, Ozhan is asking, how did you transfer monolayers and stacks onto the TM grid? Is it difficult to handle oil or spinning PMMA?
Yeah, I think we spent around 1 week to figure out this. So yeah, with a simple water resistant transfer, you can do the transfer. And yeah, if you want to get of course, good imaging, you need to also take care of the cleaning after the transfer. So we do some annealing under argon, hydrogen, or vacuum conditions. So I'm happy to give the details if he contacts me, if he give his contact information, or he just send me email.
Okay, excellent. Thank you. And there was one other question. I think it refers mostly to the beginning of your talk, where you talked about the superconductivity in 2D materials. Superconductivity at which temperature?
Oh,
comment on this?
Yeah, these materials, they are called magic angle materials. So if you have two graphene sheets on top of each other, and then if you twist them with a 1.1 degree, and then superconductivity appears, critical temperatures around 1.5 Kelvin. So it's like extremely low, but it gives like it's really a deep topic. So, but you can control the TC as well by changing number of the layers, and that's the whole motivation. So if you keep twisting them and then until the bulk, so there are some theoretical predictions that you can even go to room temperature magnetism. So it's one of the hottest research topic right now in the research of 2D materials indeed.
Okay, it seems like there's quite an improvement since the beginning of 2D materials. Okay, and one last question from Lawrence Boscher. He's asking, can you comment on the topological properties of the material?
Yeah, so this is a good question, and this material, based on the RPS measurements, it looks like it has the type 2 Weyl properties, and it has like Dirac cones. And the issue with the experimental, the way that we are doing the transport measurements is these Dirac nodes are far away from the Fermi level. So we need to be able to dope it to be able to access these topological parts of the platinum cyanide. Yeah, it does really interesting topological properties, but they are not really that accessible with the regular oxide-based dielectric. So you need to apply the electric gate, the double electrolyte gate, to be able to access this this type of the physics. So I think it's quite unexplored, but based on the RPS measurements, we do know that it has some topological behavior.
Okay, excellent. I don't see any other questions or comments over here. I hope I don't miss any. It seems like that's all. And we would like to thank you once more with this.
It's a pleasure. Thank you so much.
Thank you for joining us. And now, after this very interesting two invited talks, I would like to move to the next one. Irene, maybe if you could already share your screen, that will be excellent. So the next speaker is René D'Amico from University of York, UK, and she is going to talk about the distributed quantum information processing with spin networks. Thank you, René.
Thank you very much. Can you for
Yes.
inviting me? Can you hear me?
Yes, that works excellent.
Fantastic. Thank you very much, Umaira. So it's a pleasure to be here. And again, thanks to the organizers for inviting me today to present our latest research on distributed quantum information processing with spin networks. I'd like to tell you about our artificial intelligence adaptive device design algorithm. And I'm Irene D'Amico from the University of York, and this work has been done in collaboration with other people, as usual, with research work. So I would say the star of the work is Jörg Mortimer, who during his undergraduate final year project actually came up with the idea of applying evolutionary algorithm to spin networks for quantum processing tasks, and also design the evolutionary part of the corresponding code, and is now doing his PhD at the ICFO in Barcelona. The other collaborators are Marta Estarellas from Kilimanjaro Quantum Tech in Barcelona and the National Institute of Informatics in Japan, and Tim Spiller from the Department of Physics of the University of York. First of all, I would like to tell you today a few words about why we want to look at quantum wires for modular and distributed quantum information processing. And in particular, I would like to tell you about using for this spin chains or spin networks, and what do we mean by spin chains and spin network. And then I will move to our new evolutionary algorithm for noise intermediate scale quantum devices. And I will give you some example of applications. Sorry, Umaira, I have, okay, I think somebody else has to admit people. I saw the, yeah, okay, I think that's been dealt with.
Yes,
So, okay.
Don't worry about it.
Fantastic. Okay, so modular quantum processing and quantum wires. Now, we are used to our, so-called classical, traditional, not really classical, but traditional computers, and we know we have tons of bits inside them. And also we have very many processors within our, for example, laptop, and they need to connect to each other. So we are used to the idea of wires within our normal computers, connecting the various processors, also simply the various modules within our computer. It is very similar for a quantum computer. We will need maybe millions of qubits for performing a really groundbreaking quantum computation. This will require very many different chips and modules, and the minimum task we need to have all these modules to act as a single entity is that the exchange, at least they exchange quantum information in a reliable way. So in the sense that at least we have a quantum wire that connects, it's able to connect to quantum processor A and quantum processor B. However, we may want to actually require something more from our quantum wire. We may want to require our quantum wire to actually do some part of the algorithm itself, or some, at least quantum processing itself. This need comes from various reasons, but a particular one related to quantum information processing is the need for entanglement, the need for entangling distant qubits. There are various reasons for this need. For example, in gate-based quantum computation, in order to perform universal quantum computation, one has to be able at least to entangle two qubits, so at least to have one, be able to perform one specific gate that produces entanglement between two qubits. And if you go to different types of quantum computation, these different ideas for quantum computation, like one-way quantum computation, then the entanglement is a resource that we really need at the beginning, because we need the whole of our qubits to be entangled in a very specific way. And then the computation is actually done by measuring the qubits, so breaking, if you like, the entanglement, this overall entanglement in very specific ways. So in general, we want to be able to produce entanglement on demand and in, let's say, cheap way within our quantum hardware. And in this sense, it is great if we can have that our quantum wire, as defined before, has also the ability, for example, to either perform a specific gate or at least to entangle two far away qubits. So the requirements we would like to have from our quantum link, something more than a quantum wire, if you like, is that it can do quantum communication, so it can transfer with high fidelity quantum information between A and B, that it can cover microscopic distances. This type of proposal is the one I'm going to talk about, is complementary to the idea of using photons for quantum communication, because certainly for large distances using optical cable and photons would be much more efficient, also from the especially from the decoherence point of view. We would like it to require little control and tuning. This is important because the least you interfere with your system during your computation, the least the probability you have to disrupt your computation, to induce decoherence in your computation. And possibly we would like our quantum link to be able, as I said before, to do some quantum processing itself. And now, since various years, it has been shown that actually the use of spin chains or spin networks is a good way to be able to implement this type of requirements. Now, about the words, we sometimes refer to spin chains, to both a linear chain and something more complicated, or like a network. And similar, we use sometimes spin networks as something that is usually more complicated than a linear chain, but also includes the linear chain. So you can find these two terminology kind of interchanged a bit in this type of literature. This is maybe the first overview, you see, from 2007 on the field, but since then also the field has expanded really a lot. So what do we mean by spin chain and spin network? We literally mean a set of one-half spins which are coupled through a certain with a certain connectivity to each other. These spins are real quantum spins, so the fact that here I have pictorially plot them as some tilt spin simply is a way to say that each of them is actually a quantum superposition of state up and state down. For example, the horizontal spin means really an equal superposition of state down and state up. So on a block sphere, it would lay on the equator. And from the point of view of qubit encoding, we encode, spin down, for example, in the 0 state and spin up in the 1 state. Of course, you choose the opposite, but let's say we do this type of encoding. And we will consider, I will refer to spin up or if you like 1, as an excitation in my system, otherwise prepared with all spin all spin down or 0, initialized as 0 at the beginning of my computation. The nice thing about this type of spin network is that actually, as a mathematical framework, it can describe very many different physical systems. For example, it could describe electrons or excitons within quantum dots, coupled, for example, by spin-spin interaction or by exciton-exciton direct or exchange interaction, so dipole type of interaction. It could indeed mean it indeed also represents the case of magnetic particles with 1/2 spin. It could represent spins on molecules, transmons, qubits, on waveguide, array of Rydberg atom, and so on and so forth. So it's a very interesting mathematical framework because the results can actually be applied and adapted to a whole host of physical implementations. I will go back to the idea of considering a system that needs little control and tuning, because in this case we have kind of pushed it to the limit. So the type of implementation I will be discussing here are such that they all use the system natural dynamics. This means I set up my couplings at the beginning of my computation according to the task I want to implement. So let's say in this case, I want to implement a transfer between spin 1 and spin n on a linear chain. So I set up my coupling at the beginning. I don't change it for the whole of my computation. And then I know that whenever I inject an excitation in spin 1, okay, in my chain, I will just need to wait, so sit down and let the system evolve, so that at a known time t, I will have that this particular excitation is transferred with high fidelity to spin n, so I can collect it to spin n. So this is the idea of using the system natural dynamics that we will use toward through this whole talk, in order to perform a certain task. Specifically here, I consider the task of perfect state transfer between spin 1 and n on a linear chain, but we will see much more generic tasks. So within the field, there have been now more and more interest, especially because experimentally there have been more and more possibility of implementing this noise intermediate scale quantum devices. So we are talking about networks of spins of the order of a few tens of spins that are coherent or coherent for enough for being able to perform some kind of task within the quantum processing type of tasks. However, as you increase the number of qubits within your network, of course, your parameter space grows exponentially, and so it becomes more and more difficult to decide what is the best connectivity, which is the best, not just connectivity, but those value of your connections, of your coupling, in order to perform a certain task, the task you want out of your network. And within this idea, this necessity really, these requirements, we had this idea to introduce an evolutionary algorithm for an automatic tuning of the parameter configuration given a certain network in order to perform a given task. So you give me the task you want from a network, we apply the algorithm, and we give you the corresponding parameter configuration that will do that particular task with high fidelity. This is the reference. And so this is the scheme, the schematic representation of the algorithm. It is a genetic algorithm. So we start from a spin network with a certain connectivity, but that is unparameterized. So for example, we could set all the links equal to 1 for the sake of it. And we also start, it's not mentioned here in the schematic, with a certain request. So we request also that the network at the end will perform a certain task. Then we populate our first generation. So the idea in a genetic algorithm is that you have a set number of generations through which you get to evolve your algorithm. For each generation, we have a set number of genomes, okay? So let's say 200 generations and 1,000 genomes within each generation. So the initial population here would mean generate randomly the first 1,000 genomes, and genome means each genome would be a particular configuration of a particular set of links for my, my network. And then we start evaluating each genome within the generation. So basically we set the simulation going for each genome within a certain length of time, because we are now studying the dynamic of our network given that particular set of links in that particular genome. And within that particular dynamic, so time window, we see which is the best fidelity, well, fidelity and time, so which is the best fitness. We'll specify what is our fitness function for each genome, and we tag each genome in according to its fitness. And now we start our evolutionary algorithm. So based on the fitness, we choose 2 parents. We breed them according to the terminology in the genetic algorithm. We generate a child. We mutate the child, so we make some mutation to the genome, and we do this this loop until we fill up the new generation, and then we will move on. If we have not reached the limit of the generation, as I said, for example, we say we go for 200 generations, we do the evolution for 200 generations. If we have not reached the limit, we go back to this loop. If we have reached the limit, then we compare our best genome, and we say, okay, this is our best genome, and this is then the answer to the initial question. So the answer to how best our spin network can perform the required task, and we spit out this answer. The type, of course, to perform a dynamics and to treat our network as a proper quantum network, we need a specific Hamiltonian. The type of Hamiltonian we have considered, spin Hamiltonian, is the XSZ Heisenberg Hamiltonian. So we have a hopping term where we can let our excitation hop between nearest neighbors. We have an on-site energy here, on-site energies, and also we have the possibility of dipole-dipole interaction between excitations. As I remind you, we consider state 1 as an excitation where we start our system with initial condition with all spin down, so all our state set to 0. Initial state is 0, 0, 0, 0, 0. This last term, of course, acts only when I have at least 2 excitations in the system, and even in that case when alpha is different from 0. As you can notice, this is a time-independent Hamiltonian. So again, the idea is that our quantum information processing required task is achieved using simply the natural dynamics of our network. We don't go and tinkle with our network. The dynamics, so our Jij, the dynamics is set by our Jij and AI, and our Jij and AI are indeed set by the genome we are using. Of course, one could use different Hamiltonians. This is the ones we have used in this case for the examples I'm going to show you. Important is the fitness function, because the fitness function is the one that tells us how good are the genomes that we are producing. The fitness function will produce, is normalized to be a number between 0 and 100. The fitness is best, is better, the closest, is the best, the closest it is to 100. And this means that it satisfies very well the protocol required or the general requirement, which can include, for example, doing a certain protocol at a certain specific time. So not just doing the protocol, but at a certain time. Out of our experience with the type of size of networks we have looked at, we have chosen, Luke has decided to choose exponential functions. They work better than polynomial functions for this specific task and this specific type of size of network. They could be chosen differently. That algorithm is really versatile. This first exponential here favor high fidelities with respect to a specific, the task that is specified. Remember, f max minus 1 is negative, okay? So the closest f is to 1, the closest, this exponential is to 1, and so the result is closest to 100. The second exponential favors short gate time, so we diminish the possibility of decoherence in this way. Tf is the time at which the maximum fidelity is reached within the simulated window. So if Tf is very small, here b is negative, again, this exponential is close to 1, and so the fitness is close to 100. So I will now jump directly to some of the examples. So the first example I cite is for you just to get the feeling of it. So in this case, we have looked at high fidelity transfer within a shoelace network. We have called this a shoelace network. And the idea, once more, is to have as perfect as possible state transfer, quantum state transfer between the qubit A, then we wait a known time, and then we get the output in the qubit G. Okay, so we have found that this task indeed can be performed by this network. It's not a given that your network can perform the task you want, of course. Can be performed with the coupling shown here on the links, and it can be performed in a pretty short time with 99.7 fidelity. However, we wanted more, of course, and so we have decided to take the same network, but actually to ask this network to perform all sorts of tasks. So again, the idea is that we input our input in one or more qubits. We sit and wait for a known time, and we get our output in one or more outputs, qubits, known qubits. And then we have asked a whole sort of tasks. For example, similar to before, we have asked, we do the input in A, we want the output in G, perfect state transfer, but at a given time, 5 times J over J max, we can do it, yeah, with very high fidelity, or at a different given time. Apologies, this is a phone call. And or we can have the input, for example, in a different qubit, but we have the output as an entanglement of 2 qubits, in this case A and G, or 2 different qubits, or actually this is a different entanglement, A minus G, and so on and so forth. And we have been able to actually show that it's possible for this particular network to produce this type of tasks in very reasonable times. But we wanted also something more complicated than that. So we wanted to produce entanglement between 2 input qubits and 2 output qubits. So we wanted to produce a specific gate, the control phase gate, which is a gate that can produce entanglement, so would allow for universal quantum computation, given a certain network. And we chose as a network the most generic one, a square network as a blank canvas. So we started, all the links were the same. And we just said we have 2 additional qubits as input and 2 additional qubits as output. Can we actually use this very generic network using our algorithm? Can we optimize it to perform a control phase gate? So input here, we wait a long time, and the network by itself, this is our requirement, produce there our control phase gate between for the states that we have used as input, and we can collect it there. So this would be again a way of entangling different processors using this network, this particular wire as a network, wire link as a network. And yes, we were able to do this. And not only this, one important thing is that, first of all, we could do it with very high fidelity, but you will have noted very quickly, clearly, that here we have very complicated requirement for the links. We are specifying our links up to 4 significant figures. This could be very, very difficult for the experimentalists to do. So we said, okay, given this optimization here, the optimization is done only once, okay, and it's done with this number of significant figures. Now, if we take and approximate these numbers by cutting down the number of significant figures, how robust is this network? So again, I cut down the number of significant figures. I'm not re-optimized the network. I'm optimizing only once here. And what we found is that indeed, for significant figure, very high fidelity. 3 significant figure, the fidelity is the same, so it's very robust. 2 significant figure, the fidelity is incredibly robust. Basically, the fidelity remains the same. I go down to 1 significant figure, the fidelity is still very, very high. And let me explain also what I mean by changing the significant figure, because it's not the usual meaning. It means, for example, if I want to go from 4 to 2 significant figure, I mean I approximate this the number on the link, so the coupling, to its nearest. I round it up to the nearest 100. So, for example, 22 would be rounded up to 0. Okay, so I would cut off this link when I go down to this. 50 would be rounded up to 1. 2416 would be rounded up to 24. So you can see that I'm really doing a very, very strong approximation. And still you can see how robust the answer is. Now, what we have found is that this type of robustness is not just for this control phase gate, which is a quite complicated operation to request, but it's quite general for the type of results we have found. And I note that in this case, we had to optimize 28 parameters. So this is quite a big task. Our parameter space was really, really big. Let me just say a few words about parallelization and scaling. The type of network we have is highly parallelizable. We have almost a linear speed up with a number of cores. So this is the typical nature of the genetic algorithm. And we have tried also to understand how, if we could say something about the performance with respect to other type of algorithms. So we have taken the case of optimizing a 10-qubit linear chain that has 9 parameters for perfect state transfer. If we do this with a randomized search, we can do it, but it takes 48 minutes, quite a bit, because this is not a big system. If we use our algorithm, okay, we can do it 5,000 times faster. This is an incredible, it's really, really a huge improvement. The only machine learning algorithm we have found on the literature that was applied to quantum processing task was a different type of task. The one that was requested was using, if I remember correctly, only 7 parameters, so anyway, similar type of parameter. And we can compare, it was also compared to randomized search. And in this case, it was able to improve the randomized search only 180 times. Again, we were able to improve 5,000 times. So we think our algorithm is really very, very good for optimizing quantum processing type of tasks. And I see already Umair appearing, so this is my summary. I've introduced you to our new genetic algorithm for designing and calibrating NISQ devices. It's very versatile, it's fast, highly parallelizable. And I gave you a few examples, but by no means these are the only examples. We're really looking for experimentalists telling us we have this network. Could we use this with that network and be able to give them the answer? And this is the reference. So thank you very much for your attention.
Okay, thank you very much, René, for this amazing talk and introducing us this very, very fast algorithm. So there are a couple of questions on the chat box over here, and then the first two is somewhat related, so let me start with them. Onur Pusuluk is asking, did you use a constant mutation rate in your genetic algorithm?
No, it's not a constant mutation rate. So the mutation rate decreases as the number of generation increases, with the idea that in this way, you can, at the beginning with a higher mutation rate, you can weed away all the bad genomes, if you like. And then by diminishing the rate of mutation as your number of generation increases, you can perfect your fidelity. You can really improve your result within better genomes, a better pool of genomes.
And the next question is from Sergey Borisnuk, that's also kind of related to that question. Did you study the different number of parents in the algorithm?
No, we did it only with 2 parents for all I'm aware of. I mean, we again, Luke worked, as I said, Luke is really the star here, as I said at the beginning. So he worked a lot also in optimizing other parameters. So optimized again for the size of the networks we were choosing and the type of tasks. So the various other parameters that are entering, for example, in the fitness function, also the form of the fitness function. So the exponential form with respect to the polynomial. But we only looked at just 2 parents. Yeah.
Okay. And the next question is from Sadi Tulkurt, and he would like to understand a little bit more the input-output terminology, and asks, what happens to the quantum state at the output state when the process completes?
Yes, the idea, so let me just go back just to get an example. Maybe the shoelace is the simplest. Sorry, it goes back a bit. So the idea is that A and B, A and G in this case, are sites in which you, as I said, input and output. So you inject in A and you collect your result in G. So the way you inject or you collect will depend on your physical implementation. You could use, for example, to inject or even to collect, you could use Rabi flopping, you could use a swap gate, you could use various things. Now, if you do not collect your output state at G at the given time, and we know the time, okay, that's the good thing, because we have calibrated in our genetic algorithm the network, we know exactly when you have to collect your state. So for example, if you're doing a perfect state transfer, we know between A and G, we know exactly when your state will arrive in G, okay? So if you're not collecting your state at G at that time or close to that time, okay, then the evolution of your network will keep going. So something else will happen to, the state of your network will change. So the idea is that at that particular instant in time, for the requirement of perfect state transfer, your state of your network is basically that the state in G is decoupled from the rest of the network, and it is the state the same quantum state, you inject it at the beginning in the input state A, but you have to collect it. It will not be frozen there. We have other type of protocols with different networks in which we have also studied the possibility of actually freezing the output in the equivalent of G, so in the output state. And we can do this with some different network and protocol and different, and again, it's a matter of optimizing your parameter within your network. So we could also do that. We haven't tried it with this particular, we haven't asked this particular task. But in this case, in the cases I've shown today, the dynamics would go on. So you really need to pick up your state in G. So we start, in all of this, we start with our system being in our system network being in the 00000 cat quantum state. And then we inject our input. By inject, I mean we modify the states. We define which are our input qubits, and we modify the state of those specific input qubits the way we like, the way we think the input should be. Then we wait, and we know that at a certain type, and at the sites that we have designed, okay, we already said those are the sign in which the sites at which we will collect our output. So we know that at the certain time that we know, we can go to those output sites to pick up the result of the computation or simply the transfer, depending what is the task for which we have optimized the network.
Okay, thank you. I think that answers all the questions that I can see on the chat here. And I think within this time, I would like to thank once more, Irene, for joining us. Thank you.
Thank you very much. I will, voila. Thank you again.
Thank you. Actually, because of the last minute change in our schedule, the first speaker couldn't deliver his talk. And now I think Debabrata is here to deliver the talk. Could you share your screen, please?
Yeah, sure.
And the next speaker is Debabrata Goswami from IIT Kanpur. And he's going to talk today about the quantum information processing with femtosecond laser-induced control.
Am I audible?
Yes, please go ahead.
Thank you. Thank you. I'm sorry, I missed my slot. It so turned out that we have a very high sudden rise of COVID, and there's a huge shortage of everything, including the vaccine. And somehow my second dose was possible to be received today, and they made a very quick notice. I had to go, and it was a huge rush, and a 15-minute affair turned out to be 2 hours. So I'm sorry I missed my schedule, but as it was very kind of the rescheduling, to be able to come back and talk to you about what we are doing. So here is the basic principle in which I'll try to say. I'm going to focus a little bit more on the experiments if possible, and but let me start off with the kind of thing that I'm going to talk to you about. So this is partly what I have given as my short summary of what I presented, and hopefully you have it in your abstract book, which says that we are going to talk about quantum information processing based on the idea of controlling quantum processes and in trying to avoid decoherence. And one of the approaches in this direction, which we have been pursuing for several years, is with using shaped ultrafast laser pulses. Our technology is something which uses an acoustic modulated Fourier transform pulse shaper, which I will explain. And it also has the capability to modulate at a very rapid rate, which is kind of something which is unique, and I will explain why this becomes useful. Now, and so this is the basic point. Let me first try to explain as to what we mean our approach. So in general, you have been exposed to quantum computing a lot, so I don't think I need to show this slide to this community, but just for completeness, this is what we have. Whenever we can manipulate quantum systems, we call it quantum information processing, and anything that can lead to information processing that is useful in computing sense, that is a quantum computing application. One of the biggest problem we have in quantum aspect is the idea of decoherence, is because although we have that great power, we do not really have a way of controlling how fast they will, how soon they will decohere, so that they will maintain their coherence, and without that we have a problem. So this is the basic background behind this. One of the things which I would like to also point out here is that since we go into not a single photon kind of a scenario, when we have too much of photons available, it is perhaps imperative to understand what would happen if there are also multi-photon processes which can simultaneously occur. And one of the cases that I have referred to in this particular case, which is a useful condition for still carrying out quantum processes without any difficulty, is the specific case when either or happens, in the sense that either you will have a single photon process, and that is maybe theoretically you might think this is not typically what happens, but generally if you think about it experimentally, you are generally having photons of certain frequency or energy. So for example, I have a laser of, let's say, 800 nanometer light, and I have a energy gap which is equivalent to the half, I mean, 400 nanometer, which requires 2 photons of that. Now, unless and until I really have those 2 photons, I will not be able to inducing any single photon transition. Under that condition, you can create a situation where those 2 particular states will still remain as a 2-level system under the 2 photon limit. And this is a very interesting approach to make a simple 2-level argument extend into multi-photon case under the presumption that a single photon condition cannot happen. And there it is possible to readdress what we talk about in a single photon condition very easily by just redefining certain terms. And that is what has been done. Before I started this entire process, we presented this in one of my earlier reviews. And this is, with that logic, you can simply solve the Liouville equation and go ahead and see how things happen. So here are a few very quick theoretical background on this area, and you are welcome to refer to my review article whenever if you would like to. And so generally what happens is that you can, under this condition, you can write down the Hamiltonian in such a way that you can readdress the two level system easily from carrying forward from a single photon principle, but using multiple photon idea. And based on that, you can see the concept of the intensity-based effect, which is, as we know, is the Rabi oscillation and other kinds of things, as we have been talking about in terms of light-matter interaction. Okay. But there is one important thing which is important to know at this point, which is that Rabi oscillation is great, and in fact, Rabi oscillation typically is also not that easy. It's a coherent induced process where if there are averaging or any other effects happening, as we all know, it will almost always lead to saturation, and you will not be able to see the nice oscillating feature between the ground and excited states. So that in itself is an issue. But even then, the other important thing is, for qubit operations, it's often not the most preferred situation. You would rather want to know whether you have the condition of being 0 or 1 rather than having an oscillating feature. So to be able to create a condition where you have very well specified zeros or ones in terms of, let's say, population distribution is one of the parameters which you are primarily interested. And if you would like to work in an experimental condition, you would also want to be careful in making sure that your system is not extremely sensitive to any changes in say any changes in the terms of, say frequency homogeneity, or means inhomogeneity, if there is a bandwidth associated with it, or many other parameters which may come, making sure that you are unable to reach the 0 or 1 condition. So it is sometimes useful to take what the NMR people have been doing all the time, is to use the adiabatic concepts, where instead of using a regular pulse, you use a pulse with certain kind of shapes, and that can give rise to the inversion processes, which is under adiabatic conditions. And you can show that you would definitely go between cycle between, you can definitely decide to be either in the ground or the excited state. So that is a total inversion versus coming back to the ground state situation. So this is one of the things which extending it to short pulses is important, because in an ultra short pulse, as we know, there's large bandwidth, and so anything that we would like to address as a single frequency condition does not work for an ultra fast laser. The delta function scenario is not something which you can achieve when we are looking at a ultra short pulse, and that has consequences when you are looking at systems where there is a possibility of a large number of systems being interacting, or worst case when you have a molecule. And the other side of the story is, if you go shorter and shorter, then you would be having the difficulty of getting into the few cycle pulse regime, which is what we are not talking about at this point, because we are using the rotating wave approximation. The rotating wave approximation allows us to use the envelope profile of the pulse rather than the oscillating feature coming into the picture. And we have also worked in this area where we have gotten into the ultra short pulses, where your envelope profile is approximation. I mean, rotating wave approximation does not work anymore, and there we have to argue how it works. But generally speaking, there is a interesting scenario which we found that even for the cases where you are close to, say, when your pulses are fairly short, and you may otherwise be in the condition of a few cycle limit, the center part of the pulse can still often satisfy the uh, the conditions which are necessary for rotating wave approximation, but it doesn't work if you go to the edges. And those are the beyond rotating wave approximation cases. In this talk, I have avoided specifically those areas to be discussed, but that's a different kind of things that can be looked at. But generally speaking, what we are talking about is the laser projectile, where we can safely use the laser as the cosine as a in the semi-classical mode. By not using the photon principle in that sense, we can have the interaction with respect to the field with the and therefore take the rotating wave approximation and see how the system interacts, and the photon properties, the state property, the population properties, and the coherences of the states, how they behave. So that is what we are looking at. When you go to a molecule, this actually extends to the concept of using a wave packet, which means that instead of using a single wavelength or a single frequency, as we call it, it will have a distribution. And there again, it so turns out that when you are using a transform limited pulse, which means that you will be having a large number of states instead of having a single eigenstate, you will have a distribution which is often called the wave packet, which spreads out because of the harmonicity or the round trip time is different for different energies. So this is the typical scenario for the wave packet picture. And there too, you can prove that it's actually interesting to come up with the modified pulses instead of using a regular Gaussian pulses which are transform limited. You could have, so there the you can see the distribution in the wave packet, for example, is interfering, and they spread out, or they have a large distribution which is all over the place. But you could in fact have a um, um, particular shape of a laser which is no longer, let's say, nice like in Gaussian, but has some different looking shape, which can end up producing a very sharp looking profile at the end. And these can be useful because then you have a well-defined state in the excited condition, which you are looking for. Otherwise, you will be having a superposition which you have no control of. So that way, preparation of state with shape pulses are also very interesting and useful. So here is the example that we were able to show theoretically in earlier days as to how you could take a pulse into the excited state and can create wave packet recurrences. And it also has advantage in terms of measuring them, because you can then easily find out how they look. Otherwise, when they are getting spread out, its population is probability goes down drastically. And all of these are based on principles where we devised the Hamiltonians in the sense that they incorporated a general class where you could use multi-photon as well as a single photon limits. And depending on the connectivity of the different states, you'd be writing out a Hamiltonian of this sort, which can then mimic molecules or systems which are heavily coupled, and you can then come up with ways of how to beat the decoherence coming up because of other states being close to each other. Or this could also mean that when multiple two-level systems are close to each other, they would also end up producing Hamiltonians of this kind. So irrespective of how you look at the problem, whether you are looking at a molecule of this sort which is going to show heavy decoherence in terms of the population leaking away, or in terms of several two-level systems which are going to just have couplings to give rise to a multi-level situation in some sort, which can also have a similar structure in the Hamiltonian. So irrespective of these, you will be having these scenarios. So we picked up a example case to study in the beginning stages to see how our approach of using a shape pulse can change or have can in fact stop this heavy beating or let's say decoherence between states. Now this is a particular case which was chosen because it was an experimental verification which was possible early, which was on Karen Zuel's work, where they had shown that there was accidentally overlap of only a few states, and the energy was able to go back and forth, and so they were able to show very nice correlations between the states population going up and down. So it was like a quantum beating which they were able to show. And so we addressed this particular system, and we could find out a Hamiltonian which mimicked quite well to the experimental data. And when we looked at it, we were able to show that in case, indeed, if we do not use a simple Gaussian pulse but a shape pulse, so this is a solution that we had solved at that time, showing that if you take a pulse which actually has a profile, which has a frequency, maybe the perfect case is to have the frequency go up slowly. So this is a simple case of, in the simplest form, you're sweeping up to the resonance, holding it there, and then coming back. This adiabatic half passage in the classic sense. And then you can, in fact, have this particular perfect two-level, the population getting locked into the state 1 and state 2, whereas all these other states are not participating. And you can have this beautiful locked condition, and once the frequency turns off, tapers off, you also see it going down. That's one way. But then the more practical case perhaps would be to take, if you have a linear chirp, which is experimentally viable, and see if this will be possible, because frequency sweep going up and doing all this is horrendously difficult. And I don't know if we can really mimic that, but definitely we can do variants of linear chirp. And so it was also found that for if this chirp is slow enough, linear region also, we could generate a region over which it was possible to lock it. So this was the deep blue color one, which goes like this, and then it goes on the other side. So it was possible to track it for at least a little while.
The last seconds, please. The time is almost up, so if you can wrap up, that will be excellent.
Okay. So I would like to now go faster and say that we have managed to show these kinds of coherent interactions between states quite a bit. Now, what I would then want to go and present to you now, by the way, linear chirping is very simple. It was often this is the Nobel Prize work of Rana, who I had worked with when I was a graduate student in the same lab for a while. But other than that, I would want to go and show you that the principle that we use is a molecular beam chamber. That's the simplest case, where you can address one molecule at a time and can do these experiments. And we have managed to show that it's possible to use a chirp pulse to do these kinds of interactions in studies. One thing which is important is to know how this works. So this is a simple chirp is easy, but if you'd like to do something more than that, a programmable one, now that's where you have to actually go through a principle which is different. Conventional electronics doesn't work because they work in nanoseconds, so you need optical help, and this is where we use a Fourier transform and reverse Fourier transform. In the Fourier plane, we use an modulator which actually programmable, and you can do a shape based on that. So based on that, we have managed to do pulse shaping. This is a technology where you can pick up the right function at the right time, and at the rest of the time you don't need to know it. So often something called a Pockels cell does the job for you. But the difficulty is that this works at a rate which is comparatively slow. So you can go up to a kilohertz with it, and for molecular systems it's fine. But if you are going to go away from this principle of using a gas vacuum chamber based system, you want to do this in, let's say, in liquids, this will not work. And there you would like to add spatial control, which is by using optical tweezers, which is what Ashkin's work is all about. So what we have done is we have actually done pulsed optical tweezers, which allows you to produce um, trapped particles with the pulse laser, and then when the particle is trapped, you can use the shape pulse to address and do interactions with it. So the advantage of pulse laser anyway in trapped case is that it can automatically show you its nonlinear process right away by without using any other laser. So a single pulse can do the job for you. And what you need then is a high rep rate thing. So the same technology, which only works for low rep rate, can now, we changed that recently. So this is the old one, which I just showed you, which is slow. But if you like to, if you do it in a way so that you can do it. So here's a big slide which should tell you. Okay, anyway. So I'll show you, this is the case what happens now. If you let it interact free flowing, you would still see that you do not get all the shapes which are correct, but you do get certain shapes which are correct. All you need to do is now to be able to catch the ones which are the right shape. So the two problems are then different. One is to allow the shape pulse syncing at time steps, which goes only up to a kilohertz. The other option is to let the traveling wave interact, and the ones that are correctly shaped, you pick them up. How do you do that part? It's picking up of the shape in the right time. There is no switch which can work that fast. So what we used is again the Fourier argument. You give a phase delay in the Fourier domain. So otherwise it looks like that, all in the same place. You cannot distinguish between the shaped pulse as well as the one which is unshaped. But if you give it a phase delay in time, in frequency domain, then you will see a time delay. And so what you can do is you can actually do a time delay to the pulse by giving a Fourier phase. And so you get your shape pulse with respect to your original pulse, which is time delayed now. And that is your purely shaped pulse that you can use to do your activity. So not only do you have an optical pulse to create your tweezer, but you also have your shape pulse to do your logic. So that is the idea, and that's what we are working on. Yep.
I think time is up, so I would like to thank once more to Devaprat Goswami also for this talk. And also I would like to thank everybody in this session for joining us. And I would like to remind once more that although you can see on the chat as well that we're going to have this question and answer with presenters of the pre-recorded and posted presenters. So please join us after your lunch at 1 p.m. In the same Zoom link. Thank you very much. Enjoy the rest of the meeting. Thank you. Bye.